very cool.
Yes. We get to appreciate that.
That's nice. So, I looked at the topics, and unfortunately, we have run out of literally everything that has to do with no integrals, or stuff that has integrals, but no boundaries.
Okay. I think we should learn boundaries then. And
Yo,
then free up some
yeah.
space.
You want to learn boundaries?
Yeah.
Alright.
I looked it up briefly, and it didn't seem that bad.
Alright.
Yeah, it just seems like the or like that's interesting.
Because like, I was learning into that with some of the homework problems we were doing. Most of them are like from an integral from A to B. So I looked them up just briefly to see if I could figure them out, and they didn't seem bad.
Yeah. It's just straight up you integrate the thing, and then you do f at A minus f at B.
Yeah. Yeah.
Except the integral, so it's capital F at A minus capital F at B. Alright, in that case, if you want to do that, we can. And it really isn't that hard.
It isn't.
It isn't. So, in that case, actually, glad that you suggested it because I want to hold off on teaching sequences and series for as long as possible
Okay.
because it's very complicated. Everyone I talk to about it says, "Oh, it's a challenging thing." So
Okay.
I want to hold off on it until I learn it in MSJC Calc 2 course,
Okay. Got it.
which I'm getting for credits. I should get some candy for you.
Candy?
Thank you. Was it? Oh.
Where did you get this?
This is my student of the month gift bag.
Oh,
With this.
what? Raising Cane's sponsor?
Yeah,
that?
they gave like a whole thing.
Why are they all over that? I'm gonna grab a Snickers because I'm not me when I'm hungry.
Yeah, improper intervals is like the next easy
Okay.
one to do. Now I have an iPad.
Oh.
It should be much easier to do stuff with this.
Level up the whole setup.
Dude, this is
Level
bougie
up.
now.
I got this out of like some garage or out of upstairs really, but it's really old because this is what my brother, who's 4 years older than me, used in middle school. So
Okay.
it's pretty old.
It's
So
perfect.
it might die or anything. I really don't know.
It's like
Which is
him.
why
It's
I'm
probably fine.
constantly having it charged right now. But hopefully it'll work.
Dude, this is sick now. This is like.
Yeah.
This is
Okay.
legit.
So improper integrals. They're really simple. But first off, I'm gonna teach you like if you on A and B.
Yeah.
The boundaries. What are they called? Alright, so you already know how to integrate. I'll just give you like a simple one. Something like this.
What should we title this?
Improper integrals. Sorry.
Just that?
Yeah, just this.
That's all.
What'd you get?
Next word.
Yeah, X squared plus C.
Ouch. Yep.
Right? Those are the concept notes I did on it earlier. Okay, so boundaries just say, well, actually, you know what? A better thing to do would be to graph this. Now, I'm gonna graph x, y, and I'll graph the integral. So that's just x squared plus c, right?
Mhm.
Let's do this. Like that, right?
if you're graphing f plus c, do you just, like when you graph it, you just assume that c is 0?
No. I'm just doing this say example c is 0.
Okay.
But you guys know how like if c is negative 1 then this thing
It would be
shifts
down 1.
down to here or up to there or whatever.
Yeah.
Right? So if you were to put a boundary on, I'll label this equals this, which means that has she taught you the capital notation?
Yes.
Sweet. Which means that this is f of x, right?
Mhm.
I'll put a little, what's it called? Restriction there. So if I was to tell you something like, say, solve f of 2 minus f of 0.
Okay.
First off, do you think it's possible to get a definite number out of this?
Yes.
Even though there's a plus c and you don't know
Oh,
this?
got it. Okay.
Do you think it's possible?
Yes, could you subtract the c?
Exactly. So you would do 2 squared plus c minus 0 squared plus c, and that gets you 4 plus c minus 0 minus c, and they cancel. See that? And you can do this for anything. You can have this as 5, 1, 3, 4, 3, 4, even that, and you would get a negative number because you're doing the lower one minus the upper one.
Mhm.
But you can do this for any time. And any time that you do f of, and let's call it b, that's a foreshadowing there, f of b minus f of a. If you have a function for f of x, capital F of x, the antiderivative, then you don't need to worry about c, because every single time it's going to cancel out.
Got
You know, if you have like, I don't know, f of 5 minus f of 2, no matter what you do, I mean, this is minus 4 plus c. Even then, it cancels out.
it. Yeah, that makes sense.
Okay, which is why, I mean, that's neat, right? You don't need to worry about it when you're doing integrals with boundaries.
Yeah.
I think is the word. Now, this right here, ooh, right.
Wow.
This right here is the same thing as saying this.
Okay.
That's it.
Yeah. Cool.
You have your boundaries here. This is your b value and this is your a value, and you write it in this is minus this. That's the exact same thing as putting it into the original function f of x, not the antiderivative, and putting those two values here and here. Lower boundary, upper boundary. A, b.
Yeah.
Right. Let's roll with these two numbers. I'm not gonna roll with these ones because 0 is too simple. That's it. That's all of integrals with boundaries.
That was easy.
Yeah. You want to do a practice problem or no?
Sure. Why not?
Sure. Okay. I'm trying to think of something that would. You know what? I'm gonna give you guys a integration by parts problem.
Okay.
So that you can prepare for that.
The like latter half of like I think like 20 something to 36 are all with boundaries.
36 onward.
Yeah, all those also have boundaries. Most of them.
Find the integral from the square root of pi over 2 to the square root of pi of theta cubed times cosine theta squared d theta.
Is the cosine squared or the theta squared in cosine?
The theta squared. Sorry. I'll write it out. This pencil might die too. This pencil's just as old as the iPad.
Okay.
Sorry, guys. Oh, I'm just coming.
There's two ways you can go about this. One is you can just solve and find the integral first and then apply your A and B values.
Mhm.
Or you can apply your A and B values consistently throughout. I'll show you the one where you do it consistently throughout because there's some new notation there.
Okay.
So what are you guys using for your U and V values?
I wanted to initially do the theta cubed is my one that I derived, so it'd be u. But I don't think that works, so I switched it to I switched it to the other one, but then that one's also being weird.
Yeah.
Because I wanted to derive theta cubed because then that goes to 1 after like 2 things, so I know for sure it would cancel out eventually.
Mm-hmm.
But then I don't know how to integrate cosine of theta squared.
I'm gonna guess that it wants you to do the chain rule first and then do integration by parts, where you would set chain rule to something like cosine of theta squared.
Mm.
Because then if you did the reverse of that and you got, I don't know, I'll try it and see what I
Because I do think you have to do it that way, because I don't think this way will ever give you a simple integral at the end.
Yeah.
But I just don't know how to integrate that.
Substitution. Let's see if we still remember this. this.
Use theta squared.
Let me keep seeing if this works out, and then I'll explain it to you, because I don't know if you're tracking like what I did to turn this into that.
I'm definitely not.
Okay. Let me just see if what I'm doing works out and gets me the value, and then I'll explain that part.
Okay.
So now I gotta do a new value.
Trig identity for cosine theta. There's one for cosine of 2 theta. I don't think so. Yeah, I should get it. Trig identities. No.
Is your method working?
No.
Okay. I'll explain this then. Right. So I'm doing chain rule or substitution. Is that what she calls it? Which one does she call it? Where you introduce a new variable.
We haven't done that.
Okay.
Technically.
I'm doing u-substitution.
Okay.
So I tried integration by parts and it didn't work.
Yeah.
Right. So I made a new variable and I said, and I called it u, and I said let u equal theta squared.
Okay.
Right. And then I put all this in terms of u. I tried to, and if it works out and I don't get any thetas left, that means I'm doing a good job, and normally it ends up working out in the end. So if I let this equal theta squared, then this theta cubed equals theta times theta squared. So that equals theta times u, right? And then cosine of theta squared is u, that's cosine of u,
That makes sense.
right? And then I'll add in this step and explain some stuff. And du equals 2 theta d theta. See that?
So then d theta equals du over 2 theta. That makes sense.
Which means if d theta equals du over 2 theta, then I replace this with that, right? So you see how I got this into that?
Yes.
Right.
Is your a and b or the squared supposed to be gone? Why?
Reason is I'm setting the entire thing in terms of u. Now, just as a general rule with integrals, vast majority of the time, your integrand and your the integration part, which is this part and this part. So this part has very little to do with this and this. These are like pairs, right? Anytime you change this, you have to change this too, because this integral is going from. I'll put it in terms of a graph and see if I can do this.
So we go from theta squared. Okay.
Say, and I'll go back to our original one of 2x. This is f of x, right?
Yep.
This is f of x dx. Now this, wait a minute. Du is called a differential, Did she tell you that term?
Yeah.
So du is a differential, du is a differential, du is a differential, d theta is a differential. Then your I don't know. She does some thing on the graph, and it's like I guess think about it this way. Sorry, that's supposed to be capital. These two values are your a and b values
Mm-hmm.
for f of x.
Yeah.
Capital F of x.
Correct.
This one. And if you change this integral right here from like, so if you change this one to something completely different like f of x du, then the graph you're gonna get has to be in terms of u. Because this value is the new one that always ends up being your new value.
Oh, so you square them because you're not taking in terms of theta, you're taking in terms of theta squared.
Mm-hmm.
I see.
This new function that I'm taking, this new integral, is a completely new graph. It's where this is u.
Mm-hmm.
Because if the differential is in terms of u, then so is my graph. But how can I plug root pi over 2 into this function in this graph if root pi over 2 is for theta?
That makes sense.
I can't do it. I have to have new values for a and b that are on the axis of u, right? This is on the axis of u. So these two values have to be in terms of u. I have to make everything, if this is in terms of u, then these have to be in terms of u.
That makes sense.
That's basically the end goal, right? So, is that, like, you look a bit confused, Matthew.
Yeah, it makes sense. So you're changing your, well, basically the x coordinate, right? Like which variable.
Yeah,
It's kind of like, I'm imagining it kind of like when we do linearization in physics, not linearization math. But when we do it in physics, how we like take the function and we instead of plugging in x, plug in like x squared plus 2. It's kind of like that. So you're changing what coordinates are based on what you did to your, like what it's in reference to the du. So like instead of writing du, you could put d of theta squared. It would be weird, but like, it would mean the same thing, right? So to get from theta to theta squared, you square it. So you do the same thing with your a and b. You square both of them. That's what I'm understanding at least.
Because if all of this is in terms of u, how can you put two values for theta and then expect to get a value that actually correlates to what you had up earlier?
Yeah.
Right? Everything has to be in terms of the same function, or else this and this is automatically, these are automatically assumed to be in terms of du once you integrate the thing with how math works. These are automatically assumed to be in terms of u.
Yeah.
So if you integrated it, but you kept these two values, then you wouldn't get the actual true value.
Yeah.
Because your range would go from here to here, rather than where it's supposed to go from, which is here to here.
Yeah.
I don't know if my scale is right, but you have
Something like that.
two very different ranges here.
Yeah.
So you need to be consistent with what value you're using to define your entire integral.
Do you know what the graph like looks like specifically, or at that point you just know like the ranges?
Which graph?
Or like for the new one. So when you have u as theta squared.
That one?
Yeah.
What the graph would look like?
Yeah.
Well, I don't know yet,
Okay.
but it's not gonna look the same as this one. It's not, because these two values are two different graphs. This one is in terms with theta here, but this one is in terms of u here, right? And they're not gonna look the same. This one might look like I'm just making up an example, it's gonna be very inaccurate, but this might look like this, and then this is gonna look like that. It's gonna be very different. But all that matters is that your value is still the same. That this value still equals this value. That's all that matters, because that's all you're looking for. So as long as that's what you're looking for, then this equals this equals that, and they're not the same. This would be like roots, and then this is the actual pi over 2.
Yeah.
And they're not the same range, but the values that you're going to get are still the same, and that's the part that counts. Okay. I don't know, you still look a bit confused.
Mhm.
I know I'm throwing a lot at you because she hasn't taught you any of this yet. She hasn't taught you u-substitution yet. But,
Yeah, so wait, okay. Just for one part that like I kinda got lost on. So when you I always so the differential, right? For d theta, when you change that to that's du over 2 theta?
d theta equals du over, yeah,
That's correct.
yeah,
Yeah.
right there, yeah.
How did that work exactly?
So what is
this?
It won't make much sense graphically. If you wanted to, I could try to do something graphically, and it would look something like this. Say, say this is you guys know how du is the instantaneous version of theta u? This is the instantaneous version of that. So this right here is theta u, and then if let's see if I can do this. As this gets smaller, is that working?
Yeah. It's
Yeah.
Okay, wait, hang on. Oh, here we go. As this gets smaller, this becomes, uh-oh. What just happened?
It just erased them.
Auto deselect erase, we've enabled the ability to I don't know, it's giving me something. I don't know. As this gets smaller, this,
Whoa.
this becomes this.
Yeah.
Right? So just for the purposes of graphing, I'll just label this as this. There we go. As that. It's not actually that, but it's becoming that.
Yeah.
And this is becoming, which was it? Where was it? Your y differential, but we don't look for that. Or in we never solve for y, but it's just a vertical differential, whether that's f or y or any other thing. That's what you're looking for. Now, you know how I was talking about like how your entire function changes?
Yeah.
Like this goes to this or whatever. If this is in terms of theta and this is in terms of u. That's because you're I don't know, like say if this right here was your root pi over 2, and this was your root pi, and then this was your pi over 2, and this was your pi. Here and here, then these two, the differential here would be d theta, right?
Mm-hmm.
But this one, like spatially, because this is pi over 2 and this is pi, the distance from here to here is a bit bigger than the distance from roots because of roots.
Yeah.
Right? So the distance from here is a bit bigger than this, which means that the distance here has to be a bit bigger. That this distance has to be a bit bigger than that distance.
Yeah.
Right. So you can't set this equal to d theta as well because it just wouldn't work. You have a different distance here. You gotta have a variable, and that's where du comes in.
Yep.
Now, this is your du value. But we said, what was it like? D theta equals du over. What was it?
2 theta.
2 theta. Okay. Which means 2. Okay. Now for this right here, u is positive. 2 theta is positive.
Correct.
Right. Which means that this right here is going to be some big number.
Yeah.
So if this, and I'm talking about in terms of regular, I don't know, like say, yeah, 2a equals b. If I just said something like this, then you know for a fact that b has to be bigger than a, right?
Yeah.
Because it was like 2 times 3 equals 6, 2 times 4 equals 8, and then each time b is bigger than a, given that they're both positive. Right?
Yeah, bigger magnitude no matter what.
Yeah, bigger magnitude. The same thing goes here. If this is a big number, then this has to be bigger than this. 2 theta times bigger.
What do you get 2 theta?
That's when you take the derivative of theta squared.
Here.
Oh, yeah, okay.
So that means that this value has to be bigger than this value, which is because this value is bigger than this value.
Yeah.
Because the distance from here to here is bigger than the distance from here to here. And that's why you have to change the differential. And yeah. I don't know.
No, I think you explained that good. That makes sense.
Okay.
Yeah, I actually really understand. I really understood it. So
Mrs. Redmond will go over it.
I'm sure. Yeah. For a week straight.
But for now, what matters is how I got from here to here.
correct.
Change all of this stuff. You have to change your differential, which means you have to change your a and b values. And you set it all in terms of u.
How did you to get from the second step to the third step? Did you just multiply by 2 theta to get the du by itself?
Where?
Between here and here.
Did I just what?
Did you multiply by 2 theta? What did you do here to get from?
Cancel. This canceled with that.
Oh, divide by 2. Got it. Okay.
At this point, I'm doing u-substitution, which isn't part of today's curriculum. So you don't need to know this,
Okay.
okay? All of this stuff I'm doing on u-substitution and how I said let u equals theta squared.
Yeah.
It's different from integration by parts. It's
Yes.
different from integration by parts has u and v. Here you just have u.
Correct.
This is u-substitution. We're not learning this today.
Correct.
The only reason I had to go through this and teach you this is accidentally because the practice problem I chose, this one, requires u-substitution.
So there is no way, because the problem is that you can't take the integral of cosine of theta squared, correct?
Yeah.
So is the only way to do that through u substitution?
Probably.
Okay.
I don't really know. But,
You can't take the integral.
Well, because if you do it, you'd end up like this, right? That's the only way that would make sense, because it would be the chain rule. But then this would give you a different thing, so it wouldn't actually be the derivative of that, so it wouldn't work. Because if you have the integral of cosine of theta, right? What's that?
Yeah, cosine negative.
Just positive. So then, if you have theta squared, right? You need theta squared. But then if you
Yeah, and if it was, oh yeah, if it was divided by 2 theta, then it would have to be a whole different thing. Like, I finally get it. There you go. So, those are interesting.
Okay. So you don't need to know any of the stuff that I just
Cool,
that I
we'll just start
tried
from
to
there.
explain. But just take this new problem.
Cool.
Pretend the last 15 minutes never happened. Okay? They didn't happen. This is your original problem,
Yep.
and this is what I want you to find.
Okay.
Alright. And remember, since you already have your original thing in terms of u, you can't let your new variables be u and v because you have double meaning there. So I'm gonna say z. Oh, wait, sorry.
Z.
Whatever you want. I'm doing z.
Okay.
I just can't do u again because I already defined that.
Oh, okay. Oh, we're just doing. Oh, you. What do you call that again?
Integration by parts.
Yeah, integration of parts. Okay.
My v's look like u's. That's not good.
You could add like a little mark at the end of your U.
Oh yeah.
Not close enough. We understand.
Okay.
I think I kind of read it as V sometimes.
Here, I'll do this. Uh-oh. Okay. Oh. Alright. So, you see how I went from here to here?
Yep.
Alright. of A and B values. Now you remember how back then I was saying you need to change the A and B values because they're no longer in terms of u, now they're in terms of something else?
Yeah.
Do you guys think I need to change them here or not?
No, because it's still in terms of u, unless that one's a dv.
This is a du. This is a du.
Okay, then I would say no.
What do you think, Matthew?
What are we looking for again? Sorry, I was writing.
You're good, you're good. This is my original integral, and this is my integrated by parts. Do I need to change these two values like I did earlier, or can I leave them?
Oh, then you can just leave it.
Because these are still for u, in terms of u, and so is all this. Nowhere do I have like a z or anything, it's still u, 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 u. Right? So, I do pi over 2. And then this is the new notation that you gotta do for something like this. You do brackets, pi over 2. What this is saying, and honestly, Mrs. Redmond will teach you this, but she just leaves it at this, which I find a bit confusing, because like, what it's saying is, you take all of this, you plug it in terms of pi, solve that,
Subtract it from the
And
point
then-
of pi over
minus all of this in terms of pi, with pi over 2.
2. Okay.
But I find it a bit confusing to use this notation, because I'm like, is that saying from like sine of u, or
Or the entire thing.
the entire thing?
Yeah.
So what I do, and you can do this too, is this.
Oh yeah.
That makes more sense to me, but it's really your choice.
That makes sense.
Now we have pi over 2 sine of pi 0 minus pi over 2 over 2 equal to 4 sine of minus 0. This is the difference that I had here. I subtracted it, and then this is this one integrated, and obviously I have to do the brackets again for these two guys.
Yes.
This is just to make my life easier, I'll cancel out the negatives first, and then this one. Leave it at that.
Yep. I did it without doing, like, I just found the indefinite first. Is that wrong?
The what?
Like, I found the integral without a, like, A and B, and then I just did, like, that integral and I plugged in pi minus, is that fine?
That works. Both of these work.
That just seems easier. But
Which one?
that seems, well, it seems more, it seems faster.
Although yours works too.
Yeah.
You can do it either way. It's your personal preference. If you do it your way though, then you don't have to keep on writing. You don't have to keep on writing pi over 2 brackets,
Yeah,
pi
it's just
over
at the
2,
end.
pi over 2 brackets. You can just do the whole thing here later and then put in your two values.
Yeah.
So I don't actually know which one's faster. One of them you don't have to write a new equation at the end saying plugging in your values.
Yeah.
But with the other one, you have to keep writing your brackets and A and B values throughout.
That's true.
Whichever you want. Right. That was basically a recap for integration by parts.
Yeah.
Right. And also the substitution. Now we gotta go into the real thing of today, which I'm just starting. Which is mind if we end at 10:45 because we started late?
I don't care.
Okay. This is gonna take some time to get through. You like the iPad?
Yeah, iPad's nice.
Yeah, I like it too. I'm surprised it still works, honestly. There are two types of improper integrals. Actually, you're probably already writing that first. I'll just keep going. I'll put this in text. That was a bad idea. Okay. Do this. I have to tell you the definition of an improper integral first.
Okay.
An improper integral, and quote me on this, write it on your paper because I'm giving you the definition. An improper integral is an integral for which the interval is infinite or for which f has an infinite discontinuity in brackets a to b. Has she covered discontinuities?
Yeah.
Sweet. Actually, dang it, no, I'm not giving the actual definition because the book doesn't have like the pretty, the blue box with like the definition thing, you know what I'm talking about?
Yeah.
It just kind of has like, it doesn't really have that, but add a / and next to the or in your definition because it can either, an improper integral either has an infinite interval or an infinite discontinuity or both.
Okay.
So add an and right there.
Yeah.
After your or.
How do I know what it is already? It's getting quicker.
Matthew has not responded to my text asking where he was, in case you're curious. So, yeah.
Okay. Let's go over the first type of improper integral. Can you see that?
Yeah.
I'm probably gonna do that font instead of this one.
Okay.
Like I can write more with this one.
We can still see that easy.
Okay. So which one did they go over first? Infinite intervals. This is what I mean by infinite interval. I mean the a and b values are negative infinity and a positive infinity.
Okay.
So it will look like this. This is an improper interval.
Will there ever be a thing where it's like from 3 to a negative infinity, something like that?
Yes.
Okay.
Yes.
So only one of the A and B has to be infinite, for
Yes.
instance. Okay.
These. I don't know, like random number 4 or anything. These are all. All of these are improper intervals. Each of them. Did she tell you how an integral is like an accumulation under the area, like the area of the curve?
I've seen all through going down.
Okay. Alright. So she's just tell you like how to find them,
Yeah, that's pretty much it.
not like the concept. Okay.
It's just the area under the curve.
Alright.
Right?
I really don't want to teach like
It's
accumulation because that is a tough concept, man. I don't think I can do
It's a
that.
thing where you take square, like rectangles, right, on the area and like make them smaller and smaller. That thing. Yeah.
Yeah, like a Riemann sum where the interval approaches 0.
Yeah.
Distance in the interval approaches 0. I'm not gonna teach that. That's
You
really
don't teach that.
complicated. Okay, but the book gives this example here, which I think is pretty cool. I don't know if we have time for it, but the cool thing is that there actually exists shapes in math that have infinite surface area but finite volume,
Okay.
which I think is pretty cool. And I'm not gonna go over that because we don't have much time.
Like some kind of fractal thing.
Yeah. Exactly.
Okay.
Oh, nice. Okay, so I'm gonna give you guys the definition of improper interval type 1, and luckily they have it in a nice blue box.
Hey, there we go.
Yeah. They split it up.
Oh, maybe you wanna put the book on like the stand, maybe.
Ooh.
Smart. Oh, this is getting legit.
Or do you want to see the book and you can copy it down for yourself and then explain it for afterwards?
Sure. It doesn't matter either way.
It's faster that way.
Yeah, I'll do it faster. Yeah.
Okay. This is the first time you'll be introduced to convergence/divergence. Gotta write all of it.
Oh my. One figure.
Let's go.
Still working?
The video is still recording. It's still recording.
What is the difference between having like negative infinity versus having nothing? Because wouldn't that just mean it has no boundaries?
Negative infinity to infinity means you're looking for a specific. Or sorry, if you have nothing, then the end result you're going to get after integrating it is a function.
Okay.
You'll get
Oh, and if you
capital
plug in, then
X.
it's gonna be a number.
Yeah.
Okay.
But if you have negative infinity to infinity, then you're going to get a number.
Got
Either
it.
that or it does not exist.
Okay.
And I'll cover that. That's a good point. I don't think I'll write the whole.
You
I
don't,
might-
you don't need to.
I might take a screenshot and then put it up here just to like put it in the meeting notes later.
Yeah.
But I'm not gonna write all
Yeah,
of
we
it.
all have the book.
Okay.
We can, yeah.
But that's a good point.
For everyone in the video, it's on page 528. I believe in you.
Nice. Okay.
Oh, that's a good. I'll put page numbers if it's on. Sorry, this definition law. Oh, particles.
I'm writing your name in stone here.
Dang.
It either equals a number or does not exist. Foreshadowing, this is very informal language I'm using right here with a pound sign.
Yeah.
But if this, or really, if here, I'll go here. If this, or this, if any of them equal a number,
Mm-hmm.
like an actual number, then you say that this is, quote, convergent. That's the key definition. Is that what they said?
Yeah, they said that.
If the limit is
They said if like the one-sided infinite ones exist and is convergent, and they said if both is convergent, then the end is a thing.
Yeah. Meanwhile, if you try and solve this after plugging in your limit and you get something that does not exist, then that means. Oh wait, sorry. What do you think I'm gonna write?
Divergent.
Exactly.
It's like the books.
Pound versus do not exist. Does not exist.
And that does not exist includes if it's like infinite, correct?
Yeah.
Okay.
Yeah. You can't ever write equals infinity.
Yeah.
You can't do that.
Just right. It's that is like any kind of discontinuity kind of thing.
Can you say limit equals infinity?
Yeah.
Alright. So So limit
Well,
as
notationally.
t approaches. And t can be anything, you don't have to write t, you can write anything. I'm just using t. If this, what did you say it was? Oh, like infinity or negative infinity?
Yeah.
Okay. Do you understand part A in the definition?
Yes.
If it exists, then because this thing right here where you set the integral to the limit, all that's doing is letting you say the limit equals infinity.
Yeah.
You can't ever go straight from here to infinity because that doesn't make any sense. So you're setting a limit, and that way, when you solve for it, it'll make sense. It's legal by
Yeah.
calculus terms. Same thing goes for B. Yeah, provided this limit exists as a finite number is found.
Is there a word, like when we do the limits, you're talking about like one-sided limits versus the entire limit? Would this be called like a one-sided integral? Or is there a name for that, or no?
No.
Okay.
Good question. So, and then you get part C. If both the integral from A and the integral to A are convergent, then the integral from negative infinity to infinity is convergent.
Yeah.
Because it's this plus this. Majority of this just goes over examples. Like if you ever, I don't know what type of question College Board is gonna ask that goes over improper integrals, but the only type of stuff that I can see is they're gonna say, the only type of question I can see is College Board CD. If I'll write down some questions I think they might ask. Determine if something like this. Sorry. Or normally, just like I don't know, like a brainstorm thing. Do you think this exists? Do you think this is convergent, this integral? Because you're going from negative infinity to infinity, which means that you're constantly adding more values of x. You're adding 1 over 1 million squared, 1 over 1 billion squared, which means you're constantly adding values, but the values are getting smaller. So do you think it's convergent or divergent?
I would assume it's convergent because as x goes to infinity, it would just go to like the 1 over x squared goes to 0. So I would assume converges at some point.
You're right. What about this? Is this convergent or divergent? I already know the answer because there's actually a specific rule on this. What do you think?
I don't see why it also wouldn't be convergent. So I'm also going to say convergent.
Yeah.
Okay. Would that not go to like, wouldn't that be 0? Because shouldn't they cancel out like on either side?
We have to solve for that though, calculus wise.
What are
Well,
you?
yeah.
What are you visualizing when you determining convergent, divergent.
Okay, so I was thinking about like, do you know that the integral is like the area under a curve?
Mm-hmm.
So if you imagine the area under 1 over x squared, yeah, so that's 1 over x squared, right? So if you imagine the area of that, when you're adding slices to the area, like as x gets bigger, the slices get really, really small to the point where all the slices being added are 0. That's what I was imagining. And then if you have 1 over x cubed, then the other side is flipped across the x-axis, which would mean to be the negative of that side. So in my head, it should be 0.
Okay.
But
Makes sense. Thank you. Oh, okay.
what about this one? Is this convergent or divergent?
Convergent.
Divergent. That's called the P rule, right? P series, P rule. There's another thing that talks that says the exact same thing. Yeah, here it is, number 2. Literally says the exact same thing.
What?
That's for a very, very specific type of integral.
If p is less than or equal to.
What is it saying there?
What does 1 over x look like? 1 over x looks like.
Now the cool thing, and you'll see, you should do a bunch of practice problems on this, is that if you know one thing is convergent, then you can do some like manipulation, I guess. Like for example, you know how this is equal to this, sort of thing. You know, so the cool thing that you can do with this formula is if you were to get some random thing like but this was 2 minus 3 x dx, and normally first thing is you can't solve this for convergence or divergence, but you could say this was equal to 2 x 0.9 dx.
And then you can say that it's divergent because it's less than 1. Okay.
What was that?
Then you could say that it's divergent, right? Because the x to the 0.9 is less than 1.
Alright. I'm going off on random stuff here. So here, let's do example number 3. Evaluate the integral from negative infinity to infinity of 1 over 1 plus x squared dx.
Sorry, what was it? 1 plus x squared?
1 over 1 plus x squared. And I'll just tell you strategy wise, when you're dealing with an improper interval and want to use a definition, which definition are you guys going to do?
Yeah.
Which definition do you think you should do?
What do you mean?
Like, you can't just straight up say like the limit of the limit as you can't put two limits in each other. You can't say something like negative infinity to infinity 1 over 1 plus x squared dx equals limit as t approaches infinity of the limit
Oh,
as
got it.
like z approaches negative infinity of the integral of t z 1 over 1 plus squared. And you can't do this.
Yeah.
Right? So how are you going to solve this? How are you going to evaluate?
Split it up into two intervals.
Exactly. So you use this. So you split it up into two intervals and you say what do you say? What's the cutoff point from like the left interval to the right interval?
0.
Sure. Whatever you want.
It could just be anything.
Yeah, anything. Oh, okay. Wait, sorry. I did this wrong.
Okay. I was confused.
Yeah. Because you still have an improper interval, so there's no point in me having made that limit. Where was it? There.
Okay.
And then from here you solve the two things, right?
Sorry.
You look confused.
How do you get that? I understand where you get to the arctan line. How do you get the values on the next line?
Which one? Like 1, 2, 3?
3.
How do I go from here to here?
Yeah.
Rather than an extra step actually. This could be kind of misleading. That's cool. what is arctan of 0?
Pi over 2?
Mm-hmm. Arctan of 0 is the theta value that gets 0, right?
Oh, what would that be? Isn't that just 0?
Mm-hmm. Because sine or cosine.
Yeah, because
So
yeah.
because okay. So minus 0